Good morning all. In the last video session, we have derived the flux linkage due to internal flux as a part of finding the inductance of a transmission line. Today we are going to derive the relation for flux linkage due to external flux. Then using the flux linkages due to both the internal flux as well as external flux, we are going to find the total flux linkage and thereafter the total inductance of a current carrying conductor. Let's find out the flux linkage due to external flux. This is actually the current carrying conductor for whom we have to find the flux linkage due to external flux. In order to find that, we will be considering a cylindrical shell at a distance x from the center of the conductor having thickness dx, just like how we have used to determine the flux linkage due to internal flux. The same steps will be followed here also. So we will be considering a cylindrical shell here, and the thickness of the cylindrical shell is represented here as dx, and the cylindrical shell is at a distance of x meters from the center of the conductor. Then we will be applying the Ampere's circuital law. According to Ampere's circuital law, the line integral of magnetic field intensity around any closed path is equal to the net current enclosed. So in this case, we will be applying this Ampere's circuital law over this cylindrical shell. Within this cylindrical shell, the net current enclosed is actually the current which is flowing through this conductor, that is I. In the previous case, that is flux linkage due to internal flux, we have considered the cylindrical shell inside the conductor portion at a distance x meters from the center. While applying the Ampere's circuital law there, the current which was enclosed by the cylindrical portion was considered to be Ix. But in this case, the cylindrical shell is considered at a point very far distance from the center of the conductor. So while applying the Ampere's circuital law, within this cylindrical section, the only current which is enclosed is the current which is flowing through this conductor. So while applying Ampere's circuital law, the line integral of magnetic field intensity around any closed path is equal to the net current enclosed, and the net current enclosed is equal to the current which is flowing through the whole portion of this conductor. From here we will be able to obtain the relation for magnetic field intensity. In the next step we will be calculating the relation for magnetic flux density by using the standard relation B is equal to nu into H. We will be substituting nu0 for nu, and instead of H we will be substituting the value Hx, then we will be getting the flux density Bx. That is the value of flux density at a point x meters from the center of the conductor. After substituting the value of Ix in this relation, we will be getting the relation of flux density as nu0 I by 2 pi x. I just wish to bring a very important thing to your notice. For the derivation of flux linkages due to both the internal flux as well as external flux, we will be using a common notation for considering the cylindrical shell. That is, the cylindrical shell in the case of internal flux linkage is also considered at a distance x meters from the center. At that time the x was very much less than r. But now in the case of while finding the flux linkage due to external flux also, we are considering the cylindrical shell which is at a distance x meters from the center. Please don't get confused with both this x. This is just a common notation which is used to represent. Please keep that in your mind. Once after finding the flux density, we will be calculating the value of magnetic flux from there. As we all know from the relation of magnetic flux density, B is equal to phi by A. So from that relation we can easily find the magnitude of flux by multiplying the magnetic flux density with the area. So we will be multiplying the magnetic flux density with the area, and then we will be getting the value of magnetic flux as nu0 I by 2 pi x dx. As the flux flowing through the cylindrical shell links completely with the current which is flowing through this conductor, the value of flux linkage in this case will be same as that of the flux which will be flowing through this cylindrical shell. So the value of flux linkage is same as that of magnitude of flux, which is derived here as nu0 I by 2 pi x dx. Now this total value of flux linkage will be extending from the surface of the conductor towards the infinitive. So we can calculate from this the total value of flux linkage by using the integration from surface of the conductor to infinitive. This is actually the flux linkage, that is the total flux linkage due to external flux alone. Further simplifying it by using the integration, you will be able to calculate the value as nu0 I by 2 pi into natural log of infinity by r. From there you can easily calculate the value of inductance due to external flux linkage by dividing this particular term with the value of current. So far we have studied the flux linkage due to external flux alone. The steps which we followed are very much similar to that of flux linkage due to internal flux. The major difference is in the way how this flux is linking with the current portion in the conductor. In the case of internal flux linkage, the flux used to link with only the current Ix, whereas in the case of external flux linkage, the flux will link with the whole current which is flowing through the conductor. As I mentioned in the previous video session, the flux will be flowing through the cylindrical shell in concentric lines. This flux will link with only that particular portion of the current which is being enclosed by the cylindrical shell. In the case of internal flux linkage, the current which was enclosed by the concentric cylindrical shell was Ix. So the flux used to link with only the current Ix of the conductor, whereas in the case of external flux linkage, the flux will be flowing through the cylindrical shell will link with the whole portion of the current which is flowing through the conductor, because this cylindrical shell encloses the complete current which is flowing through this conductor. Hope the concept of flux linkage in the case of internal flux as well as in the case of external flux is very clear for you. So overall flux linkage relation can be written as the sum of internal flux linkage and external flux linkage. Internal flux linkage is indicated by the relation nu0 I by 8 pi. Just now we have derived the relation for external flux linkage, that is integral of r to infinity nu0 I by 2 pi x dx. From both these terms we can take nu0 I by 2 pi in common, then 1 by 4 plus integral of r to infinity dx by x. Instead of this, we can write the integration value, that will be coming as natural log of infinity by r. So from this relation we can easily find the value of inductance by dividing this with current. Then we will be getting the value of total inductance as nu0 by 2 pi into 1 by 4 plus natural log of infinity by r. This 1 by 4 can also be written in terms of natural log as natural log of e raised to 1 by 4. Thereafter, while taking this e raised to 1 by 4 to the denominator, we will be getting the value of total inductance as nu0 by 2 pi natural log of infinity by r e raised to minus 1 by 4, and this r e raised to minus 1 by 4 is generally represented as r dash. So this r dash can be said to be a radius of a fictitious conductor which has no internal flux. That means the internal portion seems to be a hollow one, but the same inductance value as that of an actual conductor with radius r. That is, this is actually giving you the value of complete inductance, that is total inductance value of a conductor with radius r. That can be also represented as the inductance of a conductor which seems to be a hollow one without any internal flux linkage having radius r dash. The significance of this r dash will be coming into picture in the upcoming video sessions. As all of you are aware that a single phase system will consist of two conductors, and that two conductors are indicated here as conductor A and conductor B, and the current which will be flowing through both these conductors are exactly opposite to each other and their magnitude seems to be the same. Hence we write the relation Ia plus Ib is equal to 0, where Ia is actually the current which is flowing through conductor A and Ib is actually the current which is flowing through the conductor B. Both these conductors are placed d meters apart, where d is actually the center to center distance between both these conductors. It is also represented here. Both the conductors are of same radius value small r. This concentric lines which is represented here is actually the external flux of both these conductors. So if you consider conductor A, It will have flux linkage due to its own internal flux as well as external flux. In addition to that, it will be facing the flux linkage due to external flux of the current which is flowing through conductor B. Similarly, with the case of conductor B also, in this conductor B, it will have the internal flux and external flux linkage of this conductor itself. In addition to that, it will be having the external flux linkage of the current flowing through conductor A. So we will consider conductor A and we will calculate its inductance value. So this is actually the flux linkage of conductor A due to its own internal flux and external flux. This is also the flux linkage of conductor A due to the external flux linkage of current which is flowing through conductor B. Hence the total flux linkage of the conductor A will be the sum of these two. So that is indicated here. We have added these two terms and we have written it here. Now all of you might have thought that in the case of the external flux linkage due to the conductor B, how this term D came here. Usually in the case of finding the external flux linkage, the limits of integral was from R to infinity. But while the case of external flux linkage due to the current which is flowing through conductor B, the integral limit is from D to infinity. The answer is, whenever the current is flowing through this conductor B, external flux will occur all around this conductor from R to infinity. But that complete portion of external flux from R to infinity won't link with the conductor A. Only that particular portion of the external flux of conductor B which is extending from D to infinity will be linking with the conductor A. Therefore, while writing the flux linkage with conductor A due to the current which is flowing through the conductor B, we are considering the limits of the integration from D to infinity. Okay. So we have obtained the relation for total flux linkage associated with conductor A. In the next step, we have solved the integration. So while solving this, we will be getting the value as natural log of infinity by R. And while solving this, we will be getting the value as natural log of infinity by D. From both these terms, we can take nu 0 by 2 pi as a common one. So I have taken nu 0 by 2 pi common. So the natural log of infinity by R can be written as natural log of infinity minus natural log of R. Similarly, natural log of infinity by D can be written as natural log of infinity minus natural log of D. In both these terms, natural log of infinity is there. So if you are taking that in common, then in the bracket you will be getting IA plus IB. But in the case of a single phase two-way system, the sum of the currents, that is IA and IB, the current which is flowing through both the conductors, their sum is 0. Hence this natural log of infinity term doesn't exist. So for the simplification, we will be getting the term like this, nu 0 by 2 pi IA by 4 minus IA natural log of R minus IB natural log of D. So instead of IB, I can substitute it as minus IA. And then further simplifying, I will be getting the expression like this. From this expression, I am taking IA in common. So I will be getting it as nu 0 IA by 2 pi into 1 by 4 plus natural log of D by R. Next, you will see some simple numerical problems associated with the relations which we have learned so far. All these are direct substitution problems. Let's see the first one. A single phase line has two parallel conductors. There is a single phase two-way system, and the value of D is given as 2 meters, and the diameter of each conductor is 1.2 centimeter. You were asked to find the value of loop inductance. So the inductance per conductor can be found out by using the standard relation nu 0 by 2 pi into 1 by 4 plus natural log of D by R. After making suitable substitutions, you will be getting the value of the inductance of a conductor. Thereafter, you can find the value of loop inductance by multiplying it with 2. It's a direct substitution problem. Second one is also a single phase two-way system, and the conductors are 3 meters apart. D is given and the radius value is given as 1 centimeter. Here also you are asked to find the value of loop inductance per kilometer length. But in two conditions, in the case 1, the material of the conductor is copper. Since copper being a non-magnetic material, its relative permeability value will be 1 only. In the second case, it's very clearly given that we are using steel as the material of conductor and its relative permeability value is 100. So in the case 2, the relation for inductance of the conductor gets modified into nu0 by 2 pi into not 1 by 4. Instead of 1 by 4, you have to substitute as nu r by 4 plus natural log of d by r. That is, the relation gets modified into nu0 by 2 pi into nu r by 4 plus natural log of d by r. Thereafter, making the suitable substitutions, you will be able to find the answer. Third one, you have to do it as assignment. Nothing special in this, it's just asked that to calculate the value of loop impedance. Once after getting the value of loop inductance, you can easily calculate the value of loop impedance by multiplying it with omega, because the relation for impedance or inductive reactance is omega L. All of you must solve all these problems, and it's clear that only those who have by-hearted the final relation will be able to solve these problems. So you must be thorough with all the relations. Thank you.